going to generalize the solutions to trig equations. So come up with a formula that will create every possible solution, so not just restricting between 0 and 360. So we'll just start off with sine. So sine theta equals some ratio, which we'll call x. Now if x is positive, then we know, oh well, we'd be in the first or the second quadrant. So let's just draw that up. There it is in the first quadrant. The acute angle, because x is positive, would simply be the inverse sine of whatever x is. Now if we're in the second quadrant, the acute angle is still the inverse sine of x, but we would go 180 minus that. So our two possibilities are inverse sine of x or pi minus the inverse sine of x. That's if x is positive. If x is negative, so where we've got to be careful. The acute angle is no longer the inverse sine of x. Because remember, we're saying x is a negative number. To get the acute angle, we want a positive number. So the acute angle would actually be the inverse sine of negative x. Because negative x now would be the positive number. In the third quadrant, it would be pi plus that. In the fourth quadrant, it would be 2 pi minus that. So if x is negative, our two solutions, x plus inverse sine of negative x or 2 pi minus the inverse sine of negative x. But we know inverse sine is an odd function. So I could rewrite that and look what happens. Pi plus the inverse sine of negative x is pi minus the inverse sine of x. Same answer I got when x was positive. And 2 pi plus the inverse sine of x, which again is the same answer as when it was positive, because the first solution over there, inverse sine of x, well if I add 2 pi, it just means going around the circle, I'm in the same position. So it actually does not matter whether x is positive or x is negative, I get the same solutions. Now, each one of those solutions I could add 2 pi to, so a way of generalizing that one would be, okay, sine theta is equal to x, then theta would end up being the inverse sine of x. But notice, the first possible solution, inverse sine of x, is positive. The second possible solution, inverse sine x, we go minus inverse sine of x. The third solution would be 2 pi plus the inverse sine of x. So it's alternating, plus minus, plus minus, plus minus. Now you might remember in series when we were creating formulas, if we wanted the signs to alternate, the way we solved that was to put the coefficient out the front of -1 to the power of k. Because then, if k is an odd number, we know it's going to be negative. If it's an even number, it's going to be positive. So that sorts out our plus minus, plus minus. The other thing is the multiple of pi. Well, it starts off with no pi, then 1 pi, then 2 pi, and that pattern would continue as well. So it's just multiples of pi out the front. So there's my general solution. Pi k plus -1 to the power of k, inverse sine x, and all I've got to do is substitute in integers into k, and I could create any solution that I wanted. So that's the general solution for sine. Let's see what happens with cosine. So same idea, we're going to go cos theta equals x, x is positive. So if x is positive, I know we're in the first or the fourth quadrant. The acute angle would be inverse cos of x, so there we are in the first quadrant. In the fourth quadrant, we'd have 2 pi minus that. So there's my two possibilities, inverse cos of x or 2 pi minus the inverse cos of x. Now if x is negative, again, the acute angle now won't be inverse cos of x, it'll be inverse cos of negative x. And in the second quadrant, there we are, pi minus that. And the third quadrant, pi plus that. So pi minus inverse cos of negative x, pi plus inverse cos of negative x. Now, our relationship with inverse cos of negative x that we did, remember, it was the one that was the odd function shifted pi on 2. So we ended up with inverse cos of negative x is the same as pi minus the inverse cos of x. So if I substitute that in, look what happens. we again get the same solutions as when x was positive. So once again, doesn't matter. X could be positive, x could be negative, we're still going to get the same solutions. And then of course 2 pi, we could add on to each of those. So the pattern in this one's going to go inverse cos of x, 2 pi minus the inverse cos of x. The next one would then go 2 pi plus the inverse cos of x. Then we'd go 4 pi minus. Then we'd go 4 pi plus, and so on and so on. So to generalize that one, I'm going to have multiples of 2 pi, but plus or minus. I'm always going to be adding and subtracting from the 2 pi k. Again, where k is some integer. Well, that just leaves tan. So tan theta equals x, and let's have a look at when x is positive. So now I'm in the first quadrant and the third quadrant. So I get inverse tan of x or pi plus inverse tan of x. Now hopefully the same pattern will occur where we get the same answers when x is negative. So let's have a look. When x is less than 0, so the acute angle now is going to be the inverse tan of negative x, will be in the second quadrant or the fourth quadrant. So we get pi minus the inverse tan of minus x, 2 pi minus the inverse tan of minus x, inverse tan, odd function. So inverse tan of negative x is the same as minus the inverse tan of x. So we get pi plus inverse tan of x, or 2 pi plus inverse tan of x. So in fact, again, we have got the same answers, but this time look at the pattern. In this one, inverse tan is always positive. I've got inverse tan of x, pi plus inverse tan of x. The next one, 2 pi plus inverse tan of x, and it would keep going like that. So then I'd get 3 pi plus inverse tan of x, 4 pi plus inverse tan of x, and I could keep going and keep going. So to generalize that, we simply have got multiples of pi plus the inverse tan of x. So there are 3 general solutions. They are on the reference sheet that you get in the actual HSC itself. So if ever it does escape, I mean, it's still a good idea to try and memorise them to save time. You don't always want to be flicking backwards and forwards to reference sheets. But if you do have a mental blank, they are on the sheet that you're given in the exam, so you can look back on those. Well, let's see how we use them. So now, when I want to solve an equation like this, and notice I'm not saying theta goes in between 0 and 360. So now we're basically saying, no, I want you to create a formula, a general solution for this. So for sine, we said it was pi k plus minus 1 to the power of k, inverse sine of root 3 on 2, where k is some integer. Now let's tidy that up, because we know what the inverse sine of root 3 on 2 is. That's one of our exact values. It's 60 degrees, so that's pi on 3. But that's the best I can do. And then to generate solutions, I could sub in for k. Say they did say let's go in between 0 and 2 pi. Then how would I do it? Well, I could still do it the normal way. But if I've now got the general formula, I can just substitute numbers in. So if k equals 0, I'll get pi on 3, because pi times k would become 0. Minus 1 to the power of 0 is positive 1. So I've got pi on 3. When k equals 1, I'll get pi minus pi on 3, so 2 pi on 3. When k equals 2, I'm going to get 2 pi plus something. Well, hang on, I don't want that, because I'm in between 0 and 2 pi. So, okay, I've got my solutions. And if you're really unsure about whether you got them all, remember I started at 0. Well, have a look at what happens at negative 1 to see if that. So I'd have minus pi on 3. Well, that's going to end up negative something, so that one's not there. So I've got my 2 possible solutions. I'm not suggesting that's a way to solve these equations, by the way. But if I had the formula, okay, I'll make use of it. But I certainly wouldn't find a general formula to solve a trig equation that's between 0 and 360. I'd still do that the normal way. Okay, let's try a cosine one. So minus 1 on root 2. So it's going to be 2 pi k plus or minus the inverse cos of minus 1 on root 2. Inverse cos of minus 1 on root 2. Okay, I'm thinking of my inverse cos graph. That's the one that only gives me acute or obtuse angles. So being negative, that must be an obtuse angle. 1 on root 2, that's pi on 4, but if it's obtuse, we must be talking about 3 pi on 4. So we've got 2 pi k plus or minus 3 pi on 4, where k is some integer. Note, I don't keep writing down where k is an integer. Once I've written it on the first line, I don't have to keep every line go where k is an integer, where k. I've specified it once in my solution, that's good enough. I don't have to keep writing that down. Right, so if this one's between 0 and 2 pi, if I sub 0 in, I'll get plus or minus 3 pi and 4. Well, I don't want the minus solution, I just want the plus solution. So I've got 3 pi and 4. If I substitute 1 in, I'll get 2 pi plus or minus 3 pi and 4. Well, this time I don't want the plus solution, I only want the minus solution. So 2 pi minus 3 pi and 4, 5 pi and 4 would be the other solution. Well, I wouldn't be complete without a tan one, so let's do a tan. So tan theta is 1 on root 3, so the tan one was multiples of pi, and it was always plus. So plus the inverse tan of 1 on root 3, again, where k is an integer. Inverse tan of 1 on root 3, 1 on root 3 is 30 degrees. Pi on 6, so pi k plus pi on 6. If we're in between 0 and 2 pi, if I sub 0 in, I'll get pi on 6. Sub 1 in, I'll get pi plus pi on 6. Sub 2 in, I'm going to get 2 pi plus. Well, now it's too big, so I'll stop at the pi plus pi on 6. So pi on 6, 7 pi on 6. So now it comes to solving equations like this. Sine theta is equal to the sine 5 pi and 7. And it's just so tempting to simply say, oh, well, theta is 5 pi and 7. Well, yeah, that would be one solution. But obviously there's lots of other solutions. So now I would write it like this. Pi k plus minus 1 to the power of k, the inverse sine of the sine of 5 pi and 7. And now we have to think about the inverse sine of the sine of 5 pi and 7. 5 pi on 7 is obtuse. Now think of the inverse sine graph. The inverse sine graph only gives us answers that are either acute or negative acute. So the inverse sine of sine 5 pi and 7, 5 pi and 7 is obtuse, but we want our answer as either acute or negative acute, but in the second quadrant sine's positive, so we want the positive acute angle, which is just 2 pi and 7. So that would be my solution to that equation. And that would generate every possible solution that we could have. Cos of 2x equals to the cos pi on 9. So again, it would be tempting to say 2x is equal to pi on 9, and yes, that would be one solution. But for cosine, so 2x is 2 pi k plus or minus inverse cos of the cos of pi on 9. Pi on 9 is acute, so in this case it will cancel out and leave us with just pi on 9. So 2x is equal to 2 pi k plus or minus pi on 9, but that's 2x, we want 1x. So we get pi k plus or minus pi on 18, where k is an integer. Alright, so we shall spend the day tidying up our inverse trig